right, looks like we are recording a couple of items. Don't forget tomorrow, what is happening? You got your quiz over the material on, we just turned in on the homework. So linear and angular velocity. We're also going to have arc length, area of a sector. Make sure you're familiar with those. The big one is, of course, next week on Thursday the 25th. That's when your exam is going to be. Okay, so look for it to have the same material that I just mentioned, but also material from this current lesson, the unit circle. Specifically being able to evaluate a trig function. Okay, so yesterday we started talking about the unit circle, and in fact, here it is, a completed version. Now, there were three parts to it. We have our degrees, we have the radians, and then we have the ordered pairs for each of the 16 points. And right now, we're just starting off with these 16. Eventually, we will go ahead and expand it. Okay. But the degrees, nobody really seemed to have any difficulty with those. A full revolution is 360. A fourth of that is 90. And then we went ahead and counted 45s and 30s, so that's perfectly fine. I did go ahead and mention a few things. The 3 points that are clustered in each of the quadrants, how close are they to each other? They're 15 degrees off of each other, but 30 degrees from the closest axis. Okay. Now the radians, that's when we first started looking at some of the patterns here. If it was a multiple of 45, how'd we do this? Okay, split it up into fourths. So you'll notice right here at 45, we have pi over 4. So 1/4 pi. Then we have 2/4 pi, 3/4 pi, 4/4 pi, 5/4. Okay, then we have 6/4, 7/4, and all the way back around to 8/4 pi. All right. If it was a multiple of 30, we had to do something else. Yeah, we did it by 1/6. So 1/6 pi, 2/6, 3/6, 4/6, 5/6, half would be 6/6, and then again continuing all the way around to 12/6 pi. So the 12/6 would be the 2, of course. Okay, and then we also talked about triangles, which I believe is why the first screen was here. But out of all 12 of these triangles, remember the good news was it's just the same 2 repeated over and over again. We're either going to have this 30, 60, 90, or we're going to have this 45, 45, 90. Okay, across from 30 is always 1/2. Across from 60 is square root of 3 over 2, because we're on the unit circle. Now remember, these will change if we're not on the unit circle. And eventually we will be looking at circles with either a longer or a shorter radius. Okay, so that means the values will change. Bless you. If you have a 45, 45, 90 on the unit circle, the legs are square root of 2 over 2, okay, with a radius hypotenuse of 1. And this is one way that we figured out all these points. Now the quadrantals, those were easy enough. We're placing the unit circle on the XY coordinate plane. So this is my x-axis, we have the y-axis, right here in the very middle, that's my origin. So in order to get to this point right here, I just moved 1 to the right, but didn't move vertically. Okay. So again, I don't think anybody had any problems with the quadrantals, but let's say 30 degrees. One way we talked about this was to take that point and connect it perpendicular to the x-axis, creating a right triangle. Now, because I rotated 30 degrees, this would have to be 30, this would have to be 60. What's always across from 30, Ethan? No, I'm talking about the side length across from 30. The special right triangles that we were just talking about. Okay, Xavier, can you help him out? For this triangle, what's always across from 30? What's my length?
Like, what are you talking about?
What's the length of this side across from 30?
Do you want, like, the ratio for it?
No, I want the length.
Oh, I don't know.
Okay, Raphael, you want to help him out? 1/2. This length across from 30 is always 1/2. Okay. Stephanie, what's always across from 60? What length? Square root of 3 over 2. And then we have a radius, a hypotenuse of 1. So remember, this is just a coordinate system that I've placed a circle on top of. So if I'm starting at the origin and I want to get to this point here, well, I had to move square root of 3 over 2 right, and then up 1/2. Okay, so for each of those 12 points, remember we were talking about a triangle, one of those special right triangles, so you want to be very familiar with those. Okay, but there was another way at the end that I went ahead and showed you. All 12 of these guys right here, not the quadrantals, you'll notice every value is divided by what? They're all divided by 2, okay? So if I want to go ahead and start here in quadrant 1 on what I like to call the inside track, starting here, count 1, 2, 3, and then count 1, 2, 3 back up. So 1, 2, 3, 1, 2, 3, and then what do I do with those numerators? Yeah, take the square root, but the square root of 1 is 1. So you'll immediately have these points. Now, why is that useful? I mean, what can you then do with those points? Yeah, just start to reflect them. You can reflect these across the y-axis, you can reflect them across the x-axis, and start to get all these other points that are going to be really useful to us. Okay. In fact, has anybody started practicing? Okay, I encourage you to practice. Practice this unit circle because you're going to need it. All right. Well, with all that in mind, let's start actually talking about what we can do with the unit circle. These are the notes we got today. Trig functions of any angle. So let theta be any angle in standard position. Okay, so back up. What does standard position mean? What's that, Aiden? Okay, she's absolutely right. Standard position means we begin on the positive x-axis, and then we're either going to rotate counterclockwise or clockwise. Remember, where we stop rotating, that's the terminal side. Okay. So it's theta be any angle in standard position at a point pxy be a point on the terminal side of theta. So here's what we're going to go ahead and do. Because we're now taking the unit circle and we're putting it on your xy grid, like I was just showing you, we're not going to be looking at the side ratios in terms of adjacent, opposite, and hypotenuse anymore. We're going to go ahead and refer to those as x, y, and r. Okay, so let me go ahead and show you. This example has it being in quadrant 3. So let's say in quadrant 1, I rotate, there's my terminal side, whatever theta measure I have. Well, let's say I have a point on that terminal side where I stopped. Just like before, I'm going to use that point to create a right triangle. Okay, and just think about how you would move in a coordinate system. If I want to go from the origin to this point here, I'd have to go right x and then up y, right? And then I've got my radius, which is the hypotenuse. So what would sine of theta be? Instead of thinking about it now in terms of the opposite over the hypotenuse, sine of theta would be y over r, which is exactly what we have here. So we're basing the trig functions now on their horizontal and their vertical movements in the triangle created. We're going to start to move away from the opposite, adjacent, and hypotenuse. So same thing here. For that angle that I created theta, if I wanted cosine of theta, I would take the adjacent x and put it over the hypotenuse r. So see, I have x over r. Tangent opposite over adjacent now becomes y over x, and then the reciprocals follow. Okay, so we're no longer thinking about adjacent, hypotenuse, and opposite. We're doing it in terms of the horizontal x, the vertical y, and then your hypotenuse. Everybody okay with that? But there's one thing about this. You want to be very sure you know what quadrants the functions are positive or negative. Well, how do we know? I'm glad you asked. Okay. Here's another one of those little silly sentences, but it really helps you determine immediately where your trig functions are going to be positive. You start here, and it's just like you're counting your quadrants. You would say all students take calculus. So the first letter of every word tells you what trig function is going to be positive there. Okay. Now the only exception is the A for all. All 6 trig functions are positive in quadrant 1. All 6. Every single one of them. Okay. But the S in students, well, that stands for sine. So sine of theta, that's going to be positive in quadrant 2. What do you think the T stands for? Tangent. So tangent is going to be positive in quadrant 3, and the C is going to stand for cosine. Okay. Now, will knowing where these three trig functions are positive help me figure out where the other three trig functions are positive? What do you think? Let's say I have a number. Let's say it's a positive number, right? Give me a number. 2. Okay, positive 2. What's the reciprocal of 2? 1/2. Is the reciprocal still positive? Yeah. So wherever sine is positive, its reciprocal would have to be positive as well. So I know that cosecant is positive in the second quadrant. What would also be positive in quadrant 3? Okay, the reciprocal cotangent. And what's going to be right along cosine in quadrant 4? Secant. Now also think about this. If you know where the trig functions are always going to be positive, do we know where they're going to be negative? Well, let's see. What two quadrants is cosine positive? 1 and 4. So where would he be negative? 2 and 3. If sine can only be positive in 1 and 2, what's that mean for sine in 3 and 4? Has to be negative. Okay. Just a really easy sentence. All students take calculus. Okay. So that'll help you determine, because a lot of the problems we're going to start to look at are going to be dependent on you trying to figure out where your terminal side is going to be. And you're going to use the sign of your functions to help you figure that out. It's almost like a little puzzle. Okay. So let's take a look at a problem. Here's our first one. Let negative 4, 3 be a point on the terminal side of the angle theta in standard position. And then find the exact values of all 6 trig functions. Okay, so here's what this means. We've got an actual coordinate, negative 4, 3. So let's say I've got my XY grid here. Here's X, here's Y. What quadrant would negative 4, 3 be in? Okay, it's going to be in 2, right? X is negative, Y is positive. So let's say maybe negative 4 left, 3 up. Let's say it's right here. Let's say that's that point. Well, the problem is saying that if I start here in standard position and I go ahead and rotate where he stops, okay, the terminal side is going to have that point on it. All right, so it's going to be negative 4, 3. Now, the reference angle is going to be the theta that we're always talking about. Well, it's just like we did on the unit circle. You're going to use that point, drop it to the x-axis, and create a right triangle. Okay. Now, think about the movement within your grid. Are there any sides of this triangle that I do know? What's that, sir? The negative 4 is your what? Base, height, or radius here? It's the base. Because see, here from the origin, didn't we have to go negative 4 left and then 3 up? So I know that this base has to be negative 4. So the height would be 3. Okay. You see how using the point with the terminal side, I'm creating a right triangle. Theta is always going to be placed where the reference angle would be, between the terminal side and the x-axis. Well, this is a Pythagorean triple, so this would be a 3, 4, 5. Yeah. And if you didn't know that, just use the Pythagorean theorem. 3 squared plus negative 4 squared would equal r squared. Okay. But see, now that I have the 3 side lengths, I can list all 6 of my trig functions. Okay. For example, I want sine of theta. Okay. Now remember, we're used to sine being opposite over hypotenuse, right? But now we're doing them in terms of y, x, and r. So sine is going to be y over r. So what would that be? 3/5. And you remember what we just said a second ago? All students take calculus. The S stands for what? Sine. See, in quadrant 2, sine should be positive. Aiden? Uh-huh. Here's the thing. You are going to start to rotate here, but the triangle you create, you're going to use the reference angle. Okay? So we don't know what theta is, though. And we don't need to know. Okay. Now, when we start to evaluate trig functions, we're going to know what the reference angle is because we're going to be stopping at one of those 16 points on the unit circle. Okay, so it's one of those days where there's a lot of information, so it will all connect by the end. Okay, so it may be a little hazy right now, but I promise you it'll all come together by the end of today. All right. So now I want cosine. Well, we now know that cosine is going to be x over r. Well, what's that? Yeah, -4 over 5. And that makes sense. We know that cosine has to be negative in quadrant 2. And I just want to continue all the way down. In fact, just a side note, your happy minutes for the next couple of days, you won't have to create the triangle. The triangle will be provided, and then you'll just give me the 6 trig ratios. Okay, so there's still no math involved. We're just actually working with values now. Can anybody tell me? We know tangent is going to be y over x. So what's that? Okay, -3/4. Perfect. And now get the reciprocals. So cosecant of theta. We know that's now r over y. Hypotenuse over the opposite. So I can either take the reciprocal of my previous value, or I can go ahead and go back to the diagram. Either way, what do I get? 5/3. Reciprocal of cosine is secant, which is now r over x. So what would that be? -5/4. And we finish up, the reciprocal of tangent would be cotangent of theta. Well, we now know that's x over y. Okay, we're going to try to start moving away from adjacent over opposite. And what would that give me? -4/3. Whether you took the reciprocal of your tangent or look back at your diagram. And that's it. That's all there is to it. Questions? Yes, sir.
So whenever we are happy minutes or whatever, you want us to write down like y over r?
You don't have to. I would just go ahead and take a little more time. I would just write the ratio of the numbers. Yeah. Okay, I would just write that. Okay. Well, let's look at another one. The second example here. I'm going to change this one. I want to look at 3, -6. Okay. Let 3, -6 be a point on the terminal side of an angle theta in standard position. Okay, so what quadrant would 3, -6 be in? Fourth. Okay, so from the origin, I'd go 3 right, 6 down. So let's say maybe right here. Okay. So what this means is I'm going to start in standard position. I'm going to rotate all the way around. So when you stop, that terminal side will have the point on it. Okay. It's going to have the point on it. Now, just like before, from that point, I'm going to use the terminal side and the x-axis to create a right triangle. Okay. Now, this point is 3, -6. So what's this top length right here? It would be 3, because that's how far I had to move to the right. That's my horizontal distance. And then from here, I had to go down -6. Again, don't confuse that we're saying it's a negative distance. It's a negative length. The negative just tells you the direction you're going. Okay. Now this one, we probably want to go ahead and use the Pythagorean theorem. Okay. Unless anybody knows right off the top of their head what that's going to be. Perfect. Yes. It is 3 square roots of 5. Now, if you're not seeing that, let me just run through. 3 squared plus -6 squared is equal to the radius squared. So 9 plus 36 will give me 45 is equal to r squared. So I got to take the square root. But here's the thing on this. Don't go decimal. Work with the radical. If it's not a perfect square, simplify it. The largest perfect square that will divide 45 is 9. See, we take the square root of 9, that's where we got the 3, but the 5 has to stay as is. Okay. Now, theta is going to be the reference angle, just like it was in the previous problem. That's between the terminal side and the closest x-axis. Now here, we're going to have to do a little bit of rationalizing. Okay, but we still want the same things. All right, my horizontal is x, the vertical is y, and the hypotenuse is r. So I'm looking for sine of theta. So can anybody tell me what ratio is that? Right now, just give me the ratio, and then we'll simplify in a moment. So it is y over r, so negative 6 over 3 square roots of 5. Okay, right? Would you agree? Negative 6 over 3 square roots of 5. So now I can simplify it. 3 and negative 6, that'll become 1 and negative 2. But now I want to rationalize. So I'm going to multiply both parts by the square root of 5. And we've seen that before. Okay. So what would my final answer be? Negative 2 square root of 5 over 5. There you go. 1 down, 5 to go. Okay. Once you have the triangle, that's the toughest part. Now you just start listing your ratios. Okay. So this is, something we've done before. Cosine of theta. Okay, we just talked about he's x over r. So that would be x3 over r, 3 square root of 5. Those 3's would cancel. Leave me the 1. So can anybody tell me what my final answer should be? Okay, square root of 5 over 5. Okay, so at this point, I'm just going to go ahead and start writing, the answer. If anybody wants to see where it came from, please just say something, okay? All right, let's move on to tangent. Tangent of theta. Okay, we're no longer taking opposite over adjacent. We're taking y over x. So, Susie, what is my ratio y over x? Negative 6 divided by 3. That's exactly right. So negative 6 divided by 3 will give me negative 2. Perfect. Now let's go with the reciprocals, starting with cosecant of theta. We now know cosecant is r over y. So I want the radius over y. So can anybody just tell me final answer what it's got to be? Okay. So square root of 5 over negative 2. I'm going to go ahead and say negative square root of 5 over 2. I mean, what you said is not wrong. It's just with fractions, we either prefer the numerator or the fraction as a whole to be negative. Okay. But that is absolutely right. Now, reciprocal of cosine would be secant. And you'll notice what I'm doing here, I'm just making it as easy as possible. You can take the previous answer, flip it, and then rationalize again. But we don't have to rationalize if we just go back to the diagram in this one. So secant is now going to be r over what? X. X, there we go. So I need r over x. Well, what would that be? That's just square root of 5 because the 3's cancel. Okay. And my last one, cotangent of theta. Okay, what was it? Negative 1/2. The reciprocal of negative 2. That's it. Boom. That's exactly right. Now, I want you to kind of look at the big picture here. This problem here, it was already an example. We're not on the unit circle, but the functions still apply. Because this point right here, I can go ahead and draw a circle all the way around. See, the radius is just 3 square roots of 5. So for some problems, you will be on the unit circle. Other problems, you may not be on the unit circle. Okay. So let's see what else we got. I want to go ahead and take a minute to talk about this. Now, you don't have this in your notes, but I just want to get the idea. We took the unit circle and we placed it on top of the coordinate plane, right? We're moving vertically for the x, and we're moving horizontally for x and vertically for the y. We like our coordinates to look like this, x comma y. Well, what I'm telling you here is that with the unit circle, x is going to be cosine. We can write all of our ordered pairs like this. Instead of x comma y, we can say cosine comma sine. Whenever you think cosine, you think about the x value. Whenever you think sine, you're going to think about the y value. Okay, and let me show you why this is. Let's say we have our unit circle, okay, and we rotate someplace. It doesn't matter where. Let's say right here, okay. Now, normally on a coordinate plane, again, we say x, y, but I'm wanting to show that the coordinates are going to end up as cosine sine. So let's do exactly what we did yesterday with the unit circle. I'm going to create a right triangle, okay, this guy right here, okay. Now, here's the origin. Here's the point that I'm trying to get to, right? So first I have to move horizontally x, and then I move vertically y, right? And then we've got the radius of the circle that we're calling r. Well, let's say that that reference angle theta right there, I go ahead and take the cosine of it. Cosine of theta, well, what's the ratio that we've been using for cosine now? It's no longer adjacent over hypotenuse. It's x over r, right? So I'm going to take the x over the r. Okay. Now let's say I wanted to solve this for x. So I'm going to multiply both sides by r. Very similar to how we've solved problems in the past. So those cancel. R times the cosine of theta is equal to x. But remember, why do we call it the unit circle? The radius is 1. So if the radius is 1, what's 1 times anything? So see, I now know cosine is my x value. Okay? And you could do the exact same thing for sine. Okay? Whoop, that's not what I meant to do. We could say sine of theta. We know the ratio is y over r. Okay? And maybe on this one, we don't even need to go ahead and multiply. Remember, what is the value of r? 1. So what would y divided by 1 be? There you go. Okay. So it's very important here. If you're on the unit circle, your coordinates are going to look like this. Okay. If you're not on a unit circle, your coordinates are going to look like this. R cosine of theta, r sine of theta. So if you have a length of a radius that's longer or shorter than 1, you'll be able to find the coordinates by multiplying them by cosine and sine. But we're going to be sticking with this for a while because we're going to work on the unit circle. Okay? And now you're going to see how this connects in just a minute. Okay? I know there's probably a reason why do we need to go ahead and do that. Okay. Well, let's do this. Okay. Let's see here. Okay. What was a quadrantal? It's when the terminal sides stopped on what? On an axis, right? So if you have 0 degrees or 0 radians, that's a quadrantal. Pi over 2, 90 degrees, this one, and this one. All of these are quadrantals, right? Okay. Well, that, is something that's nothing new. We've talked about that for a while, but using a quadrantal, we're going to go ahead and evaluate our first trig function. Okay. Now, it'll probably take a few examples for you to start to get the idea. I want to determine cosine of pi. Now, because it's in radians, I'm going to go ahead and do mine in radians. So there's 0 radians, pi over 2, here's pi, 3 pi over 2, all the way back around to 2 pi, right? Okay. So I'm going to go ahead and rotate pi degrees. So here's my quadrantal that we're talking about. Okay. Now, the reason those ordered pairs are so important is because those values of x and y are what you're going to use to evaluate the trig function. The angle measure, in this case pi, it simply tells you where to stop. Okay? So at this point right here, what's that coordinate from the unit circle? Remember, what's the radius? It's -1. So wouldn't the point out here on the unit circle just be -1, 0? Okay. Remember, this is your x, and this is your y. The angle measure tells you where to stop. The trig function then tells you what to do with that ordered pair you're at. So I want cosine of pi. Okay, so it told me to stop right here. Well, remember, cosine is just x. So what's the x value where you stopped? -1. Okay. Now, it's not asking for this, but I'm going to go ahead and give it to you anyway. What if I asked you for the sine of pi? We stop at the exact same location. Now, cosine is x, but what's sine? Sine is y, and I just showed that to you, right? So the coordinate we stopped at, what's the y value? Okay. Now, this will work for all the other trig functions as well. Let's say I want tangent of pi. Now, remember, tangent's ratio was to take the y value and divide it by the x value. Well, what's the y value? 0 divided by the x. So tangent of pi should be 0. Okay. Whether it's degrees or radians, that simply tells you where to stop. The trig function then tells you what to do with the point you find there. Okay, and let me show you this. Let's say I want to go ahead and plug in cosine of pi, but now my calculator's in degrees, so if I put in pi, it's going to give me something different. So I got to go ahead and put in 180, which is equivalent, right? -1. Now I want sine of the same thing, 0. Now I want tangent of the same thing. Okay. That's how this works. Now, because we're running out of time, let me go ahead for our closer. Let me go back to the unit circle. Let me kind of see if I can help you out here. Remember, cosine is what? It's the x value. What's sine? It's the y value. So let's say I ask you for the cosine of pi over 6. Remember, the angle tells you where to stop. The trig function then tells you what to do with what you find there. So here is pi over 6. Here's the ordered pair. Cosine is what? The x. So this would be the square root of 3 over 2. Okay. Let's try this one. What's the sine of 150 degrees? Okay. So we start here. We rotate around to 150. But what does sine represent? So this coordinate you find at 150, what's the y value? Now, let me throw you a curveball. What's tangent of pi over 4? Now remember, what does tangent want you to do? It's y divided by x, right? So I rotate to pi over 4. Here's the ordered pair I find. So what's this y divided by x? This is how we evaluate trig functions. Is that starting to make sense? Now, you've just seen it, so we're going to practice this again when you come in tomorrow, okay? So, good. All right. And remember, when you're on the unit circle, if you have a trig function with a ratio that has r, well, what's r? It's just 1, okay? That's all it is. All right, excellent.